Hi, everybody. Welcome to the CanDIG Mini-Conference of April 2022. This month, we're being treated to presentations by our cohort of co-op students from the University of Waterloo. This winter was our first time welcoming 3 co-op students at once, and we greatly benefited from the energy, curiosity, and talent that they carried into our projects and team dynamics. We're deeply grateful for their contributions and their company, and today we are excited to attend their presentations of their work. Please join me in welcoming Ali Raza Zaidi, Laiba Zaman, and Niharika Srivatsa to the stage with a round of applause reacts. Thank you. All right, first, Ali is going to kick off this mini conference with his presentation on implementing GA4GH specifications in the graph query language. Ali Raza Zaidi is a second-year computer science student at Waterloo who is particularly interested in data analysis, although he shows complete enthusiasm and precision on any coding task. I know him to be a quick learner, meticulous documenter, and capable of producing well-designed and extensible implementations of challenging specifications. During his time with us, he developed, integrated, and maintained CanDIG's proof-of-concept GraphQL service. He also played an important role in the research and development of federated machine learning on the CanDIG platform. Now, please look forward to Ali's presentation on using GraphQL to implement RESTful GA4GH APIs, with special focus on the beacon specification.
Thanks for that, Yuri. So welcome everybody to my mini conference presentation for today. I'll be talking about the GA4GH API standards and how to implement the RESTful specifications in GraphQL, and we'll take a close look at the GA4GH beacon service. So without further ado, let's get started. So let's just talk a little bit about the background information. So some other people have covered these topics in their own mini conferences, so we'll keep this section brief. So let's start with GraphQL. So oftentimes, many of you may be wondering what really is GraphQL. Well, I'm sure many of you have heard of REST. And so both REST and GraphQL are tools that can be leveraged to make APIs. The differences between them is that GraphQL isn't really an architectural style like REST is. It's rather a query language and a server-side runtime to fulfill said queries. It only supports JSON, and it only ever exposes one endpoint, and this is pretty different to REST, which can support multiple different output types and usually has multiple endpoints. The query language is used by the client to specify which fields they wish to get, and it returns those fields and exactly those fields only. GraphQL is language and data service agnostic, and hence it's very versatile. At CanDIG, we've built our GraphQL interface using Python and specifically the Strawberry module. This module just provides an interface for us to define code-first schemas, so we don't really have to deal with the GraphQL schema language at all. We can, in fact, just write everything in Python, and the Strawberry module will convert that into the schema language for us. So now we'll take a look at an example. Next slide, please. Nope. Previous one.
Sorry about that. Is this right?
Yeah, thank you. We'll just take a look at an example of why GraphQL may be useful to have if we already have REST endpoints. Let's take a look at an example where we want to figure out we want to have the nutritional label of a specific dish at a restaurant. With REST, we may first need to find a list of those restaurants and find their restaurant IDs. From that information, we have to parse through and find out the ID for a specific restaurant's dishes. And then we may have to find the ID of that specific dish. And then finally, we can use that ID to find the endpoint for the nutritional label. As you can see, that's several different requests that we have to make just to find one specific piece of information. Whereas with GraphQL, we can perform nested queries to find the same information, but only using one request. So this makes GraphQL a lot easier to deal with for both application developers as well as people just looking for information. And so the problem that we're facing here with REST is called underfetching, since each endpoint doesn't provide enough data for our query. A similar problem is known as overfetching, where each endpoint provides extraneous data that isn't really related to the query we're looking for. And GraphQL solves both of these by only returning the data that is required. This helps developers build applications efficiently, and for applications like machine learning or federated learning, where lots of clean data is required to train a model with any sort of confidence, GraphQL can really reduce the pre-processing work that is required, since it only returns the data that's needed. Next slide, please. So let's just talk a little bit about the GA4GH standards. So as I'm sure most of you are aware, the CanDIG organization bases several of their APIs on these standards and infrastructure set up by GA4GH. So CanDIG uses these standards and we build on top of them. We build our own layers on top of them and provide said services, for example, the CanDIG variant service. These standards are often built with RESTful applications in mind. And an example would be the GA4GH Beacon API, which we'll be talking more about later. This standard is pretty much just used to query information about specific alleles. And an important thing to note about this is that it actually doesn't have a CanDIG v2 Beacon REST service built in right now. So that kind of leads into our problem statement, which is, next slide, please. Yep, so our problem statement, which is given that we have our beacon service that we'd like to implement because of its usefulness towards genomic research, as well as implementing GraphQL because of its usefulness towards machine learning, we want to implement a beacon service that uses GraphQL. Now, we have to keep in mind that given the differences between REST and GraphQL services, we may not get every intricacy of the original replicated, but it's important to see that we can at least try and implement the core functionality. So for existing services that we've already translated to GraphQL, the way we did it was we utilized their REST endpoints and collected the data and deserialized them and returned it to the clients as per their requirements. Now, obviously, this requires the REST endpoints to be running as separate microservices. This is usually not an issue for the CanDIG v2 stack. Unfortunately, we won't have the same luxury here, considering the beacon service doesn't have a microservice in CanDIG v2, and so we'll have to implement the logic within GraphQL. But what exactly is the logic for beacon, and what does beacon actually entail? Well, for starters, the Beacon v2 endpoint and Beacon v1 endpoint are part of specifications for the Beacon service, which in essence takes allele characteristics such as the starting and ending positions of an allele and returns whether or not said allele exists within a population set. So the v1 spec is pretty standard and basic about this, whereas the v2 spec expands on this and allows for more filtering opportunities. Now, there are several challenges that we may encounter while trying to implement the beacon spec in GraphQL. For starters, if we're working with our example here today, we're just building a prototype version, so we're not going to be using a data backend, and the fields that are related to a data backend won't be implemented or easy to implement, at least in our GraphQL service. Additionally, as we've mentioned, GraphQL is pretty different from REST, and it can't support the same type of things that it supports, that REST can support. And so there are several fields that we may not have a one-to-one translation for. But that doesn't mean that GraphQL is all bad necessarily. There's still several opportunities that we can gain from this as well. For starters, Beacon v2 would be pretty easy to implement, given GraphQL's nature as a filtering and querying service. Additionally, we can make use of the existing GraphQL code that we have for the Katsu metadata service and the CanDIG variant service, considering the Katsu metadata service holds patient clinical information and the CanDIG variant service holds allele information. And so by combining the two, we essentially create a beacon service of our own in GraphQL. So let's move on to actually implementing this service in GraphQL. So the first and most critical step is actually choosing the fields. So this step actually doesn't require any coding, but it's pretty important in that we understand that we may not be able to use all the fields of the original specification in GraphQL. So we have to try and find the fields that retain the core functionality while also providing a way that works within GraphQL. So first, for example, we can't use the variant type field in the beacon request object, given that this information is inaccessible from the GraphQL implementation of the CanDIG variant service. So we're going to try and keep most of the fields in place, but certain other fields like the variant type that I just mentioned, we can drop those out since they're not that essential to the functionality. So if we look at the next slide, we can see that this is the beacon request objects fields, and we've chosen to keep 6 of them that correspond to the core functionality, like the starting and ending positions that I mentioned earlier. And we're dropping certain fields like variant type and include dataset responses because of their logistic reasons. We're dropping certain other fields like start min, start max, and things like that, just because they're really complex for just our basic task over here. And evidently we can go and implement these later on. They're mostly used for fuzzy matches when we don't have an exact starting and ending position. But for our purposes, we'll keep them out for now. So that takes us into the second step, where we're going to actually use the fields that we've selected and build the schemas for them. So building schemas in for GraphQL with our Strawberry module is pretty easy. It uses a form or a similar way of building schemas that like Python data classes use. And so we'll just use the selected fields and essentially build classes for them for each object that we're using. Now, once we've built our schemas, we can also add external facing documentation. And this is really useful for GraphQL, given that our clients need to be able to understand how to access the information, given that GraphQL isn't as common as REST's, as of right now, at least. And then once we've built our schemas, we can save the files and store them in the same location as our other GraphQL schemas, or at least just in a location where our app can access them so that we can use them later on. And finally, we just have to make sure we also add the information to the query object so that we can query our beacon objects. So this is just an example of the schema that we're using. So obviously this is pretty simple. Python, we're using decorators here. We're using classes, type hints, things of that nature. Obviously the Strawberry code we're using here allows Strawberry to take our code and define it in terms of the GraphQL schema language. But essentially it's really easy and not too difficult to implement our schemas within Python and then within GraphQL. Once we've built our schemas, the next step is to take our services and actually implement the base logic of them. So this step, I've named it connect services, but it'll depend on the implementation you're trying to pull off. Over here, I'm trying to use just basic services without a data backend. But if you wanted to implement a data backend, this would be the part where you actually build the logic for connecting to your database. At least in our case over here, we're just going to perform cross-service queries between Katsu metadata service and the CanDIG variant service within our function. And the logic here will be pretty simple. We're just going to take the user's input, clean it up a little, send it to the variant service, and then based on the response, we're going to compare that to the patients who are specified in the Katsu metadata service, and then return the response to the users as required. So if we look at the next slide, we can see that 3 lines of code here, just a small snippet of the beacon resolver function that we have. The first line is simply just to get the variant information from the CanDIG variant service given the input. The second step takes those responses and compares it to the individuals who are present in the Katsu metadata service. And then the third line is simply used to return the response based on the encoded value that we got from whether or not the individuals were present. And that actually wraps up our entire implementation of the beacon specification. So obviously this is a beacon mimicking service. It doesn't work the same way necessarily. There's still certain fields, for example, like the fuzzy matching fields that we left out. However, most of the core functionality is still kept in place, and the benefits of using GraphQL are gained. So for applications like machine learning and federated learning, this is, I'd say, at least a pretty net benefit in their aspect. Now, it is important to note that this is slightly slower than a conventional beacon REST API. That's partially because we're only we're using lots of HTTP requests to get the data from the Katsu metadata service and the CanDIG variant service. If we actually implemented a real service with a data backend, then that process is much likely to be a lot faster in that aspect. And speaking of which, why don't we take a look at some of the improvements and next steps that we can make to our implementation. So in terms of both beacon and in terms of GraphQL, in terms of beacon, for starters, we could try and implement our v2 spec. once it gets officially released. We could also try implementing our V1 spec, some of the fields like the fuzzy matches fields that we left off earlier. And obviously we can try and include a real data backend instead of the Katsu metadata service and CanDIG variant service. As for the Beacon GraphQL, we also want to maybe try using it, considering it's one of our main motivators for building this service in the first place. So it'd be nice to at least see the fruits of our labor in that aspect. And at least for the GraphQL service in general, not specific to Beacon, we may want to try implementing additional REST services. The format for them would be pretty similar, and there's many GA4GH services that don't have CanDIG v2 microservices, so we could try and implement them in the same way. And that wraps up my presentation for today. Thank you all for listening. These are just a list of the sources that I used, but I'd like to take any questions that you guys might have for me now.
I can start off with a question if there aren't any raised hands, which I can't see very well because I'm sharing the screen. Could you tell us a little bit more about like the filtering that you mentioned being a part of the Beacon v2 specification and how you would approach implementing it with GraphQL?
Sure. So the Beacon v2 specifications filtering ability is mainly to be able to filter by characteristics of patients, like their age, their gender, attributes of that nature. And so implementing this within GraphQL is pretty easy, because all we need to do is take a look at our Beacon request object, and we simply need to build an additional field within it that takes in, for example, or we can name it something like the patient information. So yep, or yeah, just I guess like further down where we were creating the schema. Yeah, so over here we can see that we've built it so far with 6 different fields. But if we wanted to, we could add another field here that would be called like personal information, and we could define its type to be an individual type. So an individual has already been like the individual type has been defined for the Katsu metadata service already, so we could just copy the definition from there. But that would allow us to use the fields that we have and filter by specific characteristics, such as their age, their gender, their race, ethnicity, whatever fields from Katsu are available. We can try and filter by that. And so essentially what happens is that once we've added that field, if the user queries by that field, GraphQL will first get a list of all the responses, and then it'll make sure that all of the fields that have been input are actually corresponding to the outputs or corresponding to the filters that we have. So for example, in our filter, if we have specified like the gender as male, then it'll collect all the list of responses, and then it'll check to see if a filter is present. If the filter is present, then it'll just return those that make the filter true, which in our case would be the subjects who have a male gender. And so that's kind of the way we would implement it here.
Awesome. Thank you very much.